Here in exercise 2, we want to use the ladder height method to find an explicit expression for the ruin probability for a Cramer-Lundberg process with exponential claims. Now, during lectures, the ladder height method is introduced in order to find an approximation of the ruin probability in the case where you have a Cramer-Lundberg process with heavy-tailed claims, because then the Cramer-Lundberg approximation doesn't work, and then you will have to try to find another approximation. That's what we typically use the ladder height method for. However, you can also use the ladder height method to derive the explicit expression for the ruin probability in the case with exponential claims. We have already derived this ruin probability loads of times by solving differential equations, by solving inverse Laplace transforms, by inverting Laplace transforms, and now we will use the ladder height method to find this ruin probability. In this video, I will go through the entire ladder height setup again. So if you're already familiar with that, you're welcome to skip onto the next video. The reason why I want to go through this setup again, even though we did it during sessions, is because this is important stuff, and also because the notation in the exercise is a bit confusing, because Schmidli and Jeffrey use different types of notation. So what we will do is we will proceed by using Jeffrey's notation, since that is what he introduced for you during lectures, and we will also write up this exercise in the following videos using Jeffrey's notation instead of the Schmidli notation that is used in the exercise text. So let's try to take a look at this entire ladder height method thing and what it's all about. As usual, we let the total capital be modeled by a Cramer-Lundberg process denoted by CT. And what CT is the initial capital plus the amount of premiums earned from time 0 to t minus the total claims that need to be paid out from time 0 to t. Recall that the number of claims nt is modeled by a Poisson process with arrival rate lambda, and the claim number process and the claim size process are independent, and the claim sizes are I, D, and in this case exponentially distributed. Typically what we want to find is the ruin probability, and what we mean by that is the probability that CT will go below 0 at some time point, given that the initial capital is U. Now another way to look at this is to say, well, let's remove the U part from the CT. And instead, we consider a process called X. So let X be CT minus U, given as the premiums minus the total claims. Now, the event of ruin can be expressed in terms of X in the sense that we will have ruin if and only if, well, if and only if X goes below minus U at some time point. Since that is exactly when C will be negative. So we have now expressed a vaguely different way of considering ruin. Instead of thinking of it as the total capital being smaller than U, then it is just X being smaller. Instead of considering as the total capital being smaller than 0, we now consider ruin as the event that X goes below minus U at some time point. Now the thing with the ladder height method is we will actually use the fact that X is a Kremer-Lundberg process as well. And since it is a Kremer-Lundberg process, it is what we call a strong Markov process. What we mean by that is that X has no memory. And given the information up until any time point, we know that we can start X over, and then it is just another Kremer-Lundberg process with whatever initial capital that there is there. And we will use this strong Markov property to consider the event of ruin, not as the case where X goes below minus U at some time point, but instead we will consider the event of ruin as an accumulation of multiple smaller ruin events, where each time X goes below its initial value, we say, well, that was a mini ruin, and then we will look at when X goes below that value again, and that's another mini ruin, and so on and so on. And that is what we mean by ladder heights. So it's probably easier if we use an illustration to talk about this. So let's just scroll down here. I've already got something ready. So what I've tried to draw here is a sample path for X. So as you can see, X starts in 0 and grows linearly with a premium rate C until the first claim occurs, and X then decreases by the size of the first claim, and then premium is earned until second claim occurs, and then so on and so on. So what we mean by ladder heights is, well, the first ladder time occurs when X goes below its initial value. The second ladder time occurs not when X goes below 0 again, but when X goes below the first ladder height. So what happens is X goes below its initial value here, right? So we consider this as one mini ruin event. Then we say, now a new Kremer-Lundberg process starts here. When does this process achieve ruin? Well, that happens when it goes below its own initial value. And this is then what we call the second ladder time. And the difference between the first ladder height and this value down here is the second ladder height. Now note that X needs to go below the value minus U for ruin to occur. So the thing is, if we keep counting the ladder heights as such, we can see that the third ladder time actually occurs here, and thus this is the third ladder height. If we keep counting these ladder times and adding up the ladder heights, then we have actually written up ruin in a way that is more complicated than before, but maybe easier to calculate. So ruin happens if and only if the sum of ladder heights the sum of ladder heights in total exceed U in size. And when I say the sum of ladder heights, we need a variable to denote the number of ladder heights we observe, and that is K. So this is number of observed ladder heights. The reason why K is something that makes sense to talk about is because, well, in this scenario, for example, things just start going better and better and better. And maybe in this sample path, the third ladder height is the last ladder height we observe. And in this case, we will then have K equal to 3. So using the ladder height method, we can deconstruct the event of ruin and reformulate it as the sum of ladder heights being greater than the initial capital. So in the ladder height method, the probability of ruin is equal to the probability of the sum of observed ladder heights being greater than the initial capital. Okay. I think we'll stop this video here because now you have actually got like an idea of what the ladder height method is. Essentially, we will then calculate the ruin probability by first finding a distribution for K, then a distribution for L, and then a distribution for this compound sum, and then finding the probability that this variable is greater than U. In the next video, we will go through some of the properties of these ladder times and ladder heights, and also introduce the concept of an inter-ladder height time, which we'll denote by tau. I think Jeffrey has a minus here, so let's just add that for good measure. See you in the next video.